It's my honor to present our work in the conference here. My name is Ruiqi. Our topic is cryptographic algorithms identification based on deep learning. The report consists of 4 parts. First, the introduction, which describes the background, academic value of our paper, some work and the motivation. Second, the methodology. It describes the main context of our paper, including the technique, model, and the experiment process. Third, the results and discussion illustrate our achievement and, most importantly, some essential analysis about our technique. And for the last one, we give a brief and clear conclusion about our contribution. We should give you a vivid description for the whole process. First, the introduction. Please look at this comic picture. This is a process of correspondence based on cryptographic protection. Alice here sent the message through the public channel to Bob, and Bob received it and decrypt it properly and get the plain text. However, Eve here, she tried to intercept the message illegally. So she must recover the keys. But she first ought to know the encryption algorithm in advance. By means of many methods like code reverse analyze or side channel attack, we can lock the range of algorithms along with our identification technique. We can finally get to know the algorithms precisely. Second, crowd engineer. These people tend to acquire some secret documents from internet, while they are always protected by encryption systems. So in order to break the system, they should know the useful information as much as possible. So identifying the algorithms also means very essential for them. Hence, we know in cryptanalysis, identifying the algorithms is the very first and vital step for recovering the keys. Third is the laboratory review. First is the initial stage. In 1998, Ramzan proved that the neural network could be used for identifying the cryptographic algorithms, and he used the perceptual for experiments, which is a primary work. Second, for the development process, during 2000 to 2016, many scholars like Dilip, Manjula, and Nellos used many machine learning models such as random trees, bagging, or adabosting to identify lots of algorithms like AES or DES. Their work's accuracy could reach over 70%. When dealt with unfixed keys, their results became worse. Recently, John or Chen, they tried to identify the block ciphers in different modes. So this is the process. Next, we go to our motivation. Our motivation could be divided into 3 parts. First is we find that less work studies the situations of unfixed keys, while in reality, people usually use different keys to encrypt. Second, the formal work cannot give a detailed explanation about how to apply such technique effectively. Third, it is necessary to use some more powerful deep neural network for identifying the algorithm, as we all know that deep learning has been applied in many aspects. So next, let's get to the second part, the methodology. Our target is to identify the unknown algorithms using deep learning methods. So how to achieve it? We're inspired by the following. First, we can see that in these pictures, the model would try to find out all the vehicles in the image. This is what we call image recognition. For the second is speech recognition. Obviously, it transformed the speech into words. So similarly, in our research, the objects are the function f, map plaintext P to ciphertext C. According to the above, these things are all belong to pattern recognition, which include, feature engineering and identification models and so on. So we designed our model with three main parts, see in figure 1. First is we're collecting the original data. Second is the feature engineering. And third, we set up the classifications model. And finally, we get the output. The whole process includes training phase and testing phase. The first stage is collecting the data. We know the ciphertext. We know that the modern cryptography could be divided into asymmetric and symmetric, while the symmetric could be divided into block ciphers, string ciphers, or hash functions. Here, our experimental objects are listed here. We know that AES, Kexue, present, Simon, and the public key algorithms are RSA and L gamma, such 6 algorithms. First, we use such 6 algorithms to encrypt the plaintext, and then we encode the ciphertext files to binary format. Each file is split into subfiles with random lengths, as the length of ciphertext is not considered in our work. We note that the key we use is strictly randomly generated in each time of encryption. And our plaintext source is from the Open American Corpus, which the size is around 1 GB. So here is, you can see the ciphertext and the encoded ciphertext subfile. It is a binary format. After obtaining the original data ciphertext, we come into the next stage, the feature engineering. So how to extract the features of original data is very crucial. Even though we know that neural network could automatically extract the features, we think if we manage to do this process manually, it will improve the results. So in 2000, NIST published a series of indices to test the randomness of sequence. These indices are also very useful in our work. We choose them as the feature indices. In this part, 3 indices are selected. We listed here. First, frequency within blocks, runs, and third, the serial index. The frequency within blocks extract the sum of 0 and 1 in each block of sequence. We give an example here. We extract the 0 and 1 from the bit sequence and get the numerical vectors here. The rows index collects the sum of each length of row in the sequence. For example, 0, 0, 1, 1, 1, 0. 0, 1, 1, 1, 1, 0. We think it is four rows of 1. And we can get another vectors. For the third serial index, it collects this sum of all the possible subsequence. For example, m length sequence has 2 to m power kinds of subsequence, and each kind of subsequence takes up 1 dimension of the vectors. And this also makes up another vectors too. And after we obtain all of the 3 indices, we combine them together to form the virtual vectors we wanted. Attach each indices with their corresponding labels. Here we see the 0 represents AS and 1 represents Kexue, exactly. So for the last part and the most important part is our deep neural network. In 2019, Ge successfully set up a new differential distinguisher based on residual neural network, which is a huge progress in cryptanalysis. Deep residual neural network introduced a residual tower, including a convolution layer, normalization layer, and identify map. The network avoids degradation when the training loss comes to the lowest level. And most importantly, the deep structure helps it fit the nonlinear objects better. Here we list the settings of our model, including the convolution layers, the numbers of layers, and the activation functions and loss functions. Here is the structure of the network. And we input the future data into the network, split the data set into training set, testing set, and validation set. The region is 423 to 3. So we have already illustrated the process of our work. Next is the result and some analysis. And table 1 shows that the results of the identification. We use precision, recall, and accuracy as the evaluation. And judging from the table and the graphics, we can find that the precision, recall, and accuracy are generally higher than 70% and 80%, which are higher than the average, 16.7%. Different groups' results are relatively centralized, which the gaps of the precision of accuracy is less than, you can see, 10%. So according to our work, there were also several problems need to be analyzed. First, why do we choose such 3 indices? And how to select the future indices based on deep learning? In fact, we select the indices from 2 aspects. First is the dimension. These properties influence the neural network. We know that the neural network are specifically dealing with multi-dimensional data, and they behave better than low-dimensional data. So the next 15 indices could be classified into these 2 types, low-dimensional indices and multi-dimensional indices. Those dimensions lower than 2, we call them low dimension, and higher than 2, we call them the multi-dimensional indices. A second, is the channel information entropy. According to the information gains principles of deep learning, the high entropy of datasets can be dealt by network more effectively. Higher entropy means more useful information, and this is much essential for our model to find the differences among those algorithms' features. So we calculate the entropy of each indices using these formulas. Based on the results, we can also classify the indices into these two types, the low entropy and the high entropy. Here we calculate each indices entropy, and we list it here. Here we can see the serial indices entropy is higher than runs and higher than frequency within blocks, and these three indices is higher than the other indices. We conduct a comparative experiment. In this experiment, we use every single index as the only feature and perform the same experiments. Here is the experiment result. Compared with each other, this experiment verified that obviously these three indices with high entropy and dimensions behave much better than others. Of course, centrally. Second, if we combine the three indices together, it can improve the accuracy further, right? And the second question is, why do we choose residual neural network? Which network is suitable for such task, recognition task? Here, we use such 4 networks to make a comparison. Fully connected network, feed-forward network, and one-dimensional convolutional neural network, and the last one is our residual neural network. There is their structure. So to understand your target here is the key point of choosing network in the aspect of cryptography. To identify the unknown algorithms is equal to fit a non-linear complex function f, which maps plaintext to ciphertext. And after that, the model should tell us the differences among such functions. So the most important thing is to seek the differences of many nonlinear functions. While a residual neural network has been proved to be the most powerful model for fitting the nonlinear object. Compared with the network, we give another comparative experiment here, and we compare such 4 networks' accuracy. And according to these figures, we can find that, of course, certainly such network behave better than others. And we find that it has a higher accuracy and stability compared with others. And for the last part, we give a conclusion for our contributions. So our work's contribution can be concluded in 3 points. First, we effectively improve the results of identification based on deep learning. The accuracy was enhanced by more than 10%. And most importantly, we also study the unfixed case situation. Here is the comparison between our work and the others' work. You can find that our work is surely improve the results. For the second, we propose a comprehensive explanation about how to effectively solve such recognition problem in detail. The first point for feature engineering, higher dimensions and information entrophies are very useful and meaningful to feature indices. So such indices can help network behave better. Second, when the objects are nonlinear and much complex to be identified, the network should use residual structures with different layers. Third, but not least, we studied how to identify the objects of functions, which is an important supplement for pattern recognition. In fact, in many aspects, algorithm or transformation is unknown to analysts. So it is significant to provide a schedule for identifying them. For example, in numerical calculation algorithms, determine which algorithm has the best ability to fit the functions is very important for mathematics. And in the image process algorithms, distinguish which kind of algorithms are affected on the images is also very important. And last, here are our work's hardware and software settings, and my code and program can be downloaded on my GitHub. Here's my reference. And thanks for your listening.